Welcome back to Science Unlocked. Today, we're diving into the fascinating world of chemistry, specifically how we can make new molecules more efficiently.
It's always amazing how chemists find clever ways to build things at the molecular level, isn't it?
Absolutely. And a big challenge is activating CH bonds, which are usually very stable. Think of them as stubborn chemical connections.
Stubborn connections. So you need something special to break them apart and build something new?
Exactly. This paper by Chinky Binani and team titled 2 HYDROXYPYRIDINE BASE ligands as promoter in ruthenium 2 catalyzed CH bond activation by arylation reactions tackles just that.
Wow, that's a mouthful. But it sounds like they're making these stubborn bonds react with a little help from ruthenium, right?
Precisely. Ruthenium is a transition metal catalyst, often used for these kinds of reactions. But the key here is what they added to it.
Ah, the promoter part of the title. So, a booster for the catalyst?
You got it. They explored a class of molecules called 2-HYDROXYPYRIDINE-BASED ligands. These are tiny molecular assistants.
Molecular assistants, so they help the ruthenium catalyst do its job better,
Yes, they coordinate with the ruthenium, influencing how it interacts with the CH bonds. It's all about fine tuning the reaction.
and they must have tested a bunch of these assistants to find the best one, right?
They did. They screened several different ligands, labeled L1 through L6, to see their effects.
So, who was the star performer, the most effective assistant in this chemical drama?
The standout was L6, specifically 5-TRIFLUOROMETHYL, 2-HYDROXYPYRIDINE. It really made a difference.
L6, huh? What kind of difference are we talking about? Was it a small improvement or something significant?
Significant. L6 enhanced the catalytic activity for the C H bond arylation reaction by an incredible eightfold.
8 times faster. That's like putting a supercharger on your chemical reaction. Imagine the efficiency gains.
Exactly. And they also found that ligands with electron withdrawing groups like L6 were particularly effective.
So, the specific structure and electronic properties of these ligands really matter, influencing how well they promote the reaction.
Absolutely. The ligand helps facilitate the deprotonation of the CH bond, which is often the slowest step.
That's the rate limiting step, right? So, speeding that up makes the whole process much quicker.
Precisely. To understand this, they use techniques like mass spectrometry and 19F-NMR to identify intermediate species.
So, they could actually observe the different stages of the reaction, seeing how the ligand and catalyst interact.
Yes, they saw the formation of ligand coordinated ruthenium species, and then they used density functional theory or DFT calculations.
DFT, that's like using powerful computers to model the reaction, right? To confirm the experimental findings.
Exactly. The DFT calculations confirmed that L6 significantly lowered the energy barrier for the CH activation step.
That's so cool, combining experimental proof with theoretical models, factorial, and this all happens in water, which is a greener solvent, right?
Yes, using water ethanol mixtures makes the process more environmentally friendly, which is a huge bonus in chemistry.
So, this research gives us a powerful new tool for making complex molecules more efficiently and sustainably.
It really highlights the critical role of these promoter ligands in fine tuning catalytic reactions.
Absolutely. It opens up exciting possibilities for future chemical synthesis, making valuable compounds more accessible. What a breakthrough!